work. And they had no hole in it.
So your parents are trying to find a way to inflate the tire now, huh?
Uh-huh.
Well, I'm sure they will find somewhere. Oh, lefty, ladies and gentlemen. Start of our last full week of April, ladies and gentlemen. Holy cow, things are winding down. 2 months? 2 months for what?
Or 1.5 months.
Yeah, just over a month actually, but yes. So, all righty. Oops, sorry.
I couldn't do it. I wanted to so bad, but I couldn't. Yeah. And I was like, yeah, it's kind of lame, by the way. Only 14 minutes playing Conceptual. I'm sorry, but I had to do it. I was having fun.
My mom lost my name.
I woke up and I was thinking many hours.
But I knew, like, with my shiny
So I literally
you all see my cards.
Wait, did you notice today? I missed her by the strokes.
Yeah, good thing.
Yep. Yeah, that's my
I would have been standing right there, straight up.
I think we all have the same list. I've seen her home this weekend
Really?
either,
Why?
so. No. I started a little bit.
And then he said,
And mine, let's see if the no cards in here. It is. Thank the Jesus Lord.
Did he put it in there or did you?
No, I put it in there.
Then don't thank him, thank
But
yourself.
it's still in there.
Well, normally things are the last place you left them.
To be honest, I thought it wasn't gonna be there.
Okay.
she was wild upset.
To be honest, I thought.
All right, ladies and gentlemen, if you would, get into your computers. Go to joinpd.com and here is the code for you. Then that one probably ain't going to work either because your computer's probably too dead for it. Then that one should work because those work every single time.
Mine's at 37.
Okay, let's just run away.
Orange lemons are pretty good.
This is mine.
Orange lemon safety notice young raisins.
Come on in.
Orange lemon safety notice young raisins.
Yep.
Okay, today. You know what? Yeah, you're right. Yeah. Not enough. Yeah. Things on the other books. Yeah.
I'm gonna be it during lunch. Just.
You let them know. Yeah. Show them, girl. Oh my god. My humor has increased. That's fun. What's the time for? It's Doomsday. Doomsday. Yeah. Yes. This is gonna explode. And
All right, ladies and gentlemen, on last week, Friday, we started talking about electromagnetic radiation. We talked about the different kinds of it. We talked about the properties of it. We talked about those things. That is a lot of what will be on your quiz this week, Thursday. Okay? So please keep that in mind, ladies and gentlemen. Okay? Again, we are starting the second half of our trimester, basically. We've done units 5 and 6. We've got units 7 and 8 to go. The other day, I gave you a grade report, ladies and gentlemen. And in that grade report, I highlighted any missing work that you had. So if you have anything that is missing, it is highlighted on your grade report and needs to get turned in. Go on Infinite Campus, check things out if you don't have that grade report anymore. But if you were good on that grade report, you should be good now, ladies and gentlemen. Okay? today we're going to start talking about nuclear reactions. And nuclear reactions involve changing the parts of the atom, the protons, the neutrons, things like that. We're going to review those things today, talk about them for a little bit. I've got a worksheet for you today. There's still this worksheet from last week, Friday. We will go over it and talk about it after we are done with the stuff today. I did this morning post the answer keys for all the worksheets for the unit for you online. They weren't on there the other day, so they are out on there now. If there's something you need to look up or something you want to see, you are welcome to, ladies and gentlemen. There is a worksheet for today on atomic structure review that will be due tomorrow for you. So that's pretty much where we're at. Today our target is to be able to understand how to find the parts of an atom, because we're going to need that, because if the protons and the neutrons in the nucleus are changing, we got to be able to figure out how many protons and neutrons there were to begin with. We will not spend a whole lot of time with electrons in this unit, because electrons are chemical changes. These are these are nuclear reactions that we're getting into. But again, I told you that on the quiz on Thursday, there will be some questions similar to this, ladies and gentlemen. Which of the following waves has the highest energy? Is it radio waves, infrared, X-rays, and ultraviolet? Now, the one that is the highest of all is not on here. So of these four, which one is the highest energy wave? So you've got to think back to that chart I showed you and, okay, which ones were the high energy ones? If you're close enough, ladies and gentlemen, there's a poster with them right up there. That has all the different waves on it. You just need to remember where the high energy ones are, ladies and gentlemen. So move your dot onto which one you think is the one that has the highest energy, please. Okay, a little bit spread out. Actually, it looks almost kind of evenly spread out, ladies and gentlemen. The one that has the highest energy are X-rays. Okay, X-rays are the ones that are the most dangerous to us. They can be helpful. It is good that you get an X-ray if you think you have a broken arm, but it is bad if you are exposed to a lot of X-rays. Okay, so again, X-rays are the ones that have the highest energy because they can penetrate through skin, through muscle, through tissue, everything except bone. Okay, which of the following has the longest wavelength? Which of the following has the biggest wavelength? Radio waves, infrared, X-rays, or ultraviolet? Okay, again, we're a little bit spread out, and that's fine because we just introduced this stuff on Friday. But the one that has the longest wavelength, ladies and gentlemen, are radio and TV waves. Radio and TV waves are the longest wavelengths, okay? So they are the ones that start off our spectrum on the far side. They are waves that are thousands of feet long, okay? So they are really big waves, ladies and gentlemen, okay? Which of the following waves has the highest frequency? Now, again, if nothing else, hopefully you remember the relationship that we talked about last week. We talked about the relationship between wavelength and frequency. We talked about the relationship between wavelength and energy. We even talked about the relationship between frequency and energy. So take a guess as to which one you think has the highest frequency. Correct answer is, ladies and gentlemen, X-rays. X-rays have the highest frequency. Okay? So X-rays have the highest frequency out of all of those waves. Okay? Now, this, ladies and gentlemen, we didn't talk about this much. Okay? we did talk about how you can remember the colors of the rainbow. What was it?
Roy G. Biv.
Roy G. Biv. Okay? Now, the reason we do our spectrum this way is because the trends that we talk about, wavelength decreasing, energy increasing, frequency increasing, that fits right into Roy G. Biv. So of these two, orange and yellow are in the middle. Red and blue are the two that are on each end. Okay? Highest frequency would be the one that is furthest to the right-hand side. Which color is furthest to the right-hand side in Roy G. Biv?
Violet.
Correct, but violet is not up here. So of these four colors, which one is the one that is furthest to the right?
Gotcha.
No, I want an answer.
Oh, blue.
Blue. Roy, red, orange, yellow, green, blue. There is no indigo, there is no violet in here. So blue is the one that is the furthest to the right, meaning blue is the one that has the highest frequency, ladies and gentlemen. Okay? Blue is the one that has the highest frequency. Okay? Which is the one that has the shortest wavelength? Shortest wavelength. Now again, remember, over here, by radio and TV waves, the wavelengths are incredibly long. Over here, by gamma rays, they are really short. So again, Roy G. Biv is right in the middle there. So which one of these, red, orange, yellow, or blue, is the one that has the shortest wavelength? There should only be two that you're debating between. Okay? Because again, patterns are things that go in one direction or another. So I haven't given you patterns that it goes up and then comes back down. No. Our patterns are it's either increasing or decreasing as you move along. So that should eliminate a lot of your two of your choices here, ladies and gentlemen. So tell me, which one do you think is the shortest wavelength? Okay, good. At least we're on the right two for this question. The one that is the shortest, ladies and gentlemen, is blue. As your wavelength gets shorter, your waves have more energy and a higher frequency. They are more dangerous to us. Okay? They are more dangerous to us. All right? Which of these wavelengths has the lowest energy? Has the lowest energy? Same four choices, ladies and gentlemen. All right, lowest energy, ladies and gentlemen, that would be red light. The very first one, Roy out of Roy G. Biv. Okay? That is the one with the lowest energy. All right, so that is that, ladies and gentlemen. All right, take out your periodic tables real quick, ladies and gentlemen, or your solubility chart, wherever you can write this down, ladies and gentlemen. Take something out that you can write this down on, that you can use on your quiz or your test, ladies and gentlemen. So let's put this into a summary form for you, something that you can easily access. Oops. I'm just going to move it down. I'm not changing what I wrote, ladies and gentlemen. I'm just moving it down a little bit, just so you know. Radio and TV. Microwave.
Do we like this?
Yep. IR. IR is infrared. Sorry, I spelled that wrong, ladies and gentlemen. Let me correct it. IR is infrared. Oops. Okay. So this is the way our spectrum goes, ladies and gentlemen. And here is the thing about visible light. It is made up of Roy G. Biv. Now, I am not going to write that out, but you should know that Roy G. Biv stands for red, orange, yellow, green, blue, indigo, and violet. That is what that Roy G. Biv stands for. That is the colors of the rainbow that we see from white light above us. Okay? So that is what white light is actually made up of. Now, we talked about 3 trends, if you will, on the periodic table. And those are wavelength, by the way, the other way you will see wavelength is this symbol lambda. Okay? That is the other way you will see it expressed. As you go across the periodic table, wavelength decreases. The waves become shorter over here than they are over here. So if you have this copied onto your periodic table and you have this and the 2 other notes, one is going to be frequency, and one is going to be energy. The activity that we just did will become a lot easier for you because we're going to talk about what happens to all 3 of these as you go across the periodic table. But over here you have really long waves. Over here you have really short waves. Because the wavelength changes, ladies and gentlemen, so does the frequency. But frequency and wavelength are in an inverse relationship, meaning if wavelength is decreasing, what is frequency doing? It is increasing. So basically, ladies and gentlemen, because the waves get shorter, we see more of them pass a point in a given amount of time. Imagine if you were, ladies and gentlemen, you were broke down on the side of the road and you were waiting for someone to come and pick you up. And the traffic is just going by you. And in the far lane is semi-tractors with trailers, big long trailers. But in the front lane right next to you, ladies and gentlemen, there are little Volkswagen Beetles. Okay? One right after the other. They're all traveling at the same speed, but which one do you see more of? The big semi-tractors or the little Beetles? You might see 3 Beetles to 1 semi-tractor. Because they are smaller, you will see more of them. Does that not make sense, Kiana? Or? Well, you know the 18-wheelers that haul things around in the world?
Well, I understand like what you're saying, but like, what length? Like, what are you talking about?
Well, what we're talking about is if you have a long vehicle and it's traveling past you, you're going to see fewer of those long vehicles in a minute.
Oh, yeah, I thought you meant like as they pass by.
Well, what I'm saying is, okay, so you're standing there and you're watching the traffic go by as you're waiting for somebody. You see the trailers go by. You're bored, so you start counting them. 10 go by in a minute. That is a way of measuring frequency. How many go past in an amount of time? But in the near lane, you notice there's all small cars. So you start counting them. And while 10 semis may have gone by in a minute, you may see 30 of the littler cars. That means their frequency is higher. You see more of them in the same amount of time.
See, that makes more sense.
Good.
I thought you were talking about something.
No, I'm glad you gave me, wanted clarification. So as these waves get shorter, more waves pass a point in a given amount of time because these big long waves, even though they're moving at the same speed, it just takes a long time for you to see the whole wave. The shorter waves, a lot less time. Okay? So frequency increases. Energy also, ladies and gentlemen, increases. Okay? Energy also increases. So these things over here, we don't believe they are harmful to us. Okay? Low energy, low frequency, long wavelength. These things over here, short wavelength, high energy, high frequency. We know these are dangerous to us. We know this for a fact. You don't want to be exposed to gamma rays. You don't want to be exposed to X-rays unless you have to be. Okay? Even sunlight, you get a sunburn from it. That's your body's way of telling you, get out of the sun. You had too much. Get out. Okay? Go indoors. Okay? So these three we know can have an effect on the body. These, we don't think they can. Okay? We don't think they can. But here's the thing, ladies and gentlemen. Normally, you don't get exposed to a lot of these because they're a big, long wavelength that are flying around us. Okay? But nowadays, we have a device that draws these to you. What is that device? What? Your cell phone. Your cell phone works on a radio wave signal, which means for it to be able to be used, for you to get a call, for you to send a call, for you to text, for you to snap, for whatever you guys do, because we know calling ain't it, it needs to have a signal coming to it. So wherever you have your cell phone, ladies and gentlemen, you are drawing radiation, energy traveling in the form of a wave, to it, wherever it is right now. So gentlemen, I want you to think about where you happen to carry your cell phone. And the fact that you are bringing extra radiation to that area of your body. I'm done having kids. I don't care. Okay? But there are studies out there that say men who carry their cell phone in their front pocket have a lower sperm count than men who don't. Now, they're not saying that it is because of the radiation. They're also not saying that it's not. And if you're sitting there going, well, they would never do something like that to us. They used to put lead in paint, poisonous to people. They used to say that smoking was good for you. They used to say that artificial sweeteners didn't cause cancer in lab rats, and they were wrong on all of those, ladies and gentlemen. So we don't know what's going to happen in the next 30 years, 40 years, to the generation that has grown up with a cell phone on them. Who knows? My daughter scared the heck out of me because she told me one day, yeah, I sleep with this under my pillow at night. Why do you do that? Well, because then it'll vibrate and I'll know somebody calls. Who's calling you at 3 a.m.?
It
But
would heat up.
sitting under your pillow at night, where is it drawing all of the radiation to?
Under your head.
Your brain, your head.
And it gets
Again,
hot.
I don't care if it gets hot. I'm more worried about the fact that you are bringing extra radiation to your brain all the time, 8 hours a night when you sleep. Again, x-ray. You go in for an x-ray, they take your x-ray. That is good for you. Tells you if your arm is broken or not. But the people who work there, 5 hours or 5 days a week, 8 hours a day, they cannot be exposed to that much radiation. They leave the room. They go outside it. The room has special walls that keep the x-rays from getting out. Even when you're there, they lay a lead vest on top of you to cover parts of your body so you don't get exposed to these x-rays. Why? Because we know they can cause damage to the body. Okay? Anybody going to the spring play here at East High?
I want to.
You know what it's called? Radium Girls. Anybody know why? What the story is? Go ahead.
They used to make watches, and they used to use uranium to make it glow. And they, to make the peak of the brushes, they used to like this with it, and it had uranium on it. So eventually, like, people's jaws fell off and stuff like that. It wasn't cute.
Yes. Literally, that is a true story. Years ago, before there were digital clocks, people still wanted to read them at night. So they found a material that you could put into paint that would make it glow. Okay?
Glow sticks?
No, not like glow sticks, just like you would expose it to light, and then at night when it got dark, it would just naturally glow, which was great for a clock because you look over at 2 in the morning, you want to know what time it is, If your clock face wasn't lit up like our digital ones are now, you couldn't see anything. So to do this, they used to hand paint the dial on the clock, the numbers on it. Well, they needed very small numbers, very fine paintbrush. So the mostly ladies who were doing this, who would paint, they would lick the end of their brush to get a fine tip on it, dip it into the paint, and then paint the numbers and the little dashes on the clock. Well, they did this for years and years and years. They didn't realize that the substance that they were putting on there was radioactive. That's what caused it to glow. And literally, some of their jaws ended up falling off of their face because the radiation did such damage to the bone that their teeth were falling out, their jaws were falling off. It was not a good thing. Again, at the time, we didn't know that this was going to happen. So understand, they'll even warn pregnant women, don't stand in front of a microwave. Why? We don't believe the microwaves are getting out. But why take the chance? Why take the chance? So don't stand directly in front of a microwave when you're using it. All right? Again, there's a lot of things in the world that we say, oh, this is a great invention. This is going to revolutionize things. And sometimes it does, and other times it doesn't work out quite so well. Okay? Questions, ladies and gentlemen? All right, sorry, I get off on a tangent once in a while with those stories because they're kind of interesting. This, if you have this on your periodic table, this is going to help you on your next quiz, guaranteed. Guaranteed. Now, please remember, like in the pair deck that we just did, I didn't give you gamma rays as a choice. I only went to X-rays. Well, X-rays are the next highest in energy, the next highest in frequency. We may take 4 forms of visible light and ask you which one has the longest wavelength or shortest wavelength or things like that. And it doesn't have to be red. It might be yellow, green, blue, and indigo. But if you have this down and you have these trends down, all you got to do is look, where does it fall? Further to the left, further to the right, where does it fall? Then you can figure out which one has the longest wave, shortest wavelength, highest energy, lowest energy, things like that. Questions? All right. That is a good review of what we did last week as well, ladies and gentlemen. All right. So here's where we're at then. Okay. This is slide number 11 in your notes, your EISN. Please open it up and get to it, ladies and gentlemen. Okay. Again, we have been through the parts of the atom. We have already gone through them. I'm not going to sit here and go over everything again. But again, remember, protons, positive charge location is in the center and mass of 1 AMU. Neutrons, neutral or no charge nucleus, 1 AMU. Electrons, negative charge in the electron cloud, 0 AMUs basically. We will not talk much about electrons in here. Okay? It isn't the electrons that we're worried about in this unit. It is these two right here. Okay? Those two right there. All right. Questions? All right. So please remember, this is the vocabulary we touched on before. Again, I'm just going through it quickly with you. The nucleus is the center portion of the atom. It has a positive charge because it contains protons. It also contains neutrons, but they have no charge. So that makes it positively charged. But the nucleus is where all of the mass of an atom is stored. All of its mass, because protons and neutrons are the only part that have mass. Electrons do not have a mass compared to the protons and the neutrons. The atomic number, the number that is a whole number on your periodic table, the 21, 22, 23, 24, that is the atomic number, ladies and gentlemen. That is how many protons an atom has. Okay? And it is important that we understand that because in this unit, the number of protons in an atom can change. Before, they never could. Now they can. Okay? So, it is what tells you what kind of atom it is, and it tells you the name and the symbol. So, for example, 47 protons, that element is silver, Ag. Okay? Always. There is no other element with 47 protons. Okay? All elements start out neutral. That means the protons and the electrons are the same. Again, we're not going to worry too much about electrons. Charge of an atom is when the protons and the electrons are no longer the same. Normally that happened because we gained or lost electrons. Okay? But protons minus electrons would give you the charge of an atom. We're not going to worry about that too much. We're just going over it because it was an important thing that we talked about before. All right. Isotopes are important in this unit, ladies and gentlemen. Isotopes are important. They are atoms that have the same number of protons but a different number of neutrons. Not every atom on the periodic table is radioactive. Every element 82 and higher is. That's lead. So these big atoms, the ones that are right here, okay? The ones that are right here, number 82 and higher. These atoms, from here on out, ladies and gentlemen, all the way through the bottom of the table, are all radioactive. All of them. Every single one. However, carbon, which is here, has radioactive isotopes. Okay? Certain atoms of carbon are radioactive that are isotopes of carbon. Hydrogen even has radioactive isotopes. The difference is one hydrogen atom out of a 10,000 might be radioactive. One carbon atom out of 10,000 might be radioactive. But it is these isotopes that are radioactive. Not every carbon atom is. Okay? And isotopes are atoms that have the same number of protons but a different number of neutrons. Okay? And the isotopes of an atom can be reactive. They are still that same element. Carbon, hydrogen, whatever the element is, lead, uranium, plutonium. Okay? But they have different mass numbers. Okay? And the mass number is equal to the number of protons plus the number of neutrons. Remember, there is no way for you to find the number of neutrons of an atom if I point at it on the periodic table. You cannot do that. I have to either give you the mass number, in which case you can find the number of neutrons, or I have to give you the number of neutrons, in which case you can find the mass number. Okay? You cannot find it off of the periodic table. Okay? So hang on before we do. All right, real quickly here, ladies and gentlemen. Nope, sorry. P table. All right. This, ladies and gentlemen, is an online periodic table. Okay? Now, the advantage of an online periodic table is it will give you some information that other periodic tables will not. Okay? Other periodic tables will not. Yes. Everything that is on the top of that, all of those formulas, including the pressure are on the top. Okay. Thank you. Okay, so the nice part about this periodic table, ladies and gentlemen, is I can click it over to this part that says isotopes. And when I do, the number at the bottom down here changed. It's no longer the atomic mass. This is the original. So 1.008, 6.94, 9.0012. When I hit this button that says isotopes, now it changes to a whole number. 7, 10, 12. That is actually the number of isotopes for every one of these elements. So if we come down here to mercury, ladies and gentlemen, there are 40 different isotopes, 40 different kinds of mercury atoms in the universe. 40 different kinds. And the only thing different about them is the number of neutrons in their nucleus. Same number of protons, okay? So if you look, the only ones where you will find them with very small numbers are the last of the man-made ones here. 5, 5, 5, 4, 4, 1. Even here, 16, 20, 19, 38, 39. Hydrogen, 7. So again, there are 7 different isotopes of the element hydrogen. So if I come up here and I click on it, here they are as you go through it. Okay? These are the different isotopes, all the way to what would be hydrogen 7 with a mass of 7.052. Now again, I'm not going to make you memorize these things or anything like that. But what this tells us, ladies and gentlemen, is that there are a lot of different ways that atoms exist. Okay? A lot of different ways that atoms exist. Okay? And because of that, some of them become radioactive. All right? Some of them become radioactive. So I just wanted you to show you that so you could see that. Okay? All right. So when you look at a nuclear symbol, this is what you will see, ladies and gentlemen. This is more than just calcium. Okay? This is giving us 2 extra pieces of information. That box is highlighted for a reason, but let's start with this, ladies and gentlemen. This number up here in this symbol is the mass number. So this is an individual atom of calcium. It has a mass number of 41. Now on the periodic table, ladies and gentlemen, calcium has a mass of 40.078. So this is not what you would get off of the periodic table. That's a different mass number. This number down here, ladies and gentlemen, that is the atomic number or the number of protons. Okay? So that is telling us how many protons it has. Obviously, Ca is the element symbol. And if we take and we subtract these 2 numbers in front, ladies and gentlemen, we get the number of neutrons. Already set up for you to easily do the math of subtracting 2 numbers. And the number of neutrons is equal to the mass number minus the atomic number, because this mass number is the protons and neutrons. If you take away the number of protons, you are left with the number of neutrons. So this is the way we will write elements in this unit, ladies and gentlemen. We will put 2 numbers in front of them. By the way, great quiz material for Thursday as well. The box is there, ladies and gentlemen, because if there is a charge to an atom, that is where they would list the charge. +1, +2, +3. We've already been through that in the unit where we did the writing compounds and things like that. So you won't see a lot of charges in this unit, but if there is a charge, it would be up there, ladies and gentlemen, and that charge is equal to the number of protons minus the number of electrons.
Would it have like that, like, I can't.
Well, it would have like this.
I know. What
A -1, a -1, a -1.
Like how we created like the elements with that.
That's how we did that, like crisscross when we...
And we added like one of the, like the I.
That had to do with that naming? Yes, Zoe. But here's the thing.
We have to add that to this.
No, because we're not going to talk about compounds in this unit. We're going to talk about individual atoms. Okay? So we're not talking about compounds here. We're talking about individual atoms. Okay? Questions? Good questions, Zoe. All right. So the name of this element, ladies and gentlemen, would be calcium 41. Putting the number in here so we know what kind of isotope it is. Okay? It's not just calcium. It is specifically an atom of calcium 41. Maybe that makes it radioactive. Maybe that doesn't. But it definitely tells us or allows us to figure out how many protons and how many neutrons this atom has. Okay? So you will see a lot of symbols this way in this unit, ladies and gentlemen, with these two numbers in front. Okay? So if I were you, I would put this onto your periodic table somehow. I would copy this symbol and I would write what these numbers mean. I would write what the symbol is, and I would write how to find the number of neutrons. All right. So, now that we kind of understand that, ladies and gentlemen, for this first element here, first of all, what's Rn? On your periodic table, if you don't have your periodic tables out, now would be a great time to take them out, ladies and gentlemen. Now would be a great time to take them out, okay? Because they're going to be asking you about compounds, and it would be helpful for you to have this. All right, so what is Rn? Radon. And technically, ladies and gentlemen, this is radon
The other one's lead.
219. And this is lead 211. That would be the name of these. Okay? All right. So, 86 protons. This number on the bottom here, that is the number of protons. How many electrons would this have? Also 86. Why? If there is no charge here, these two are equal. Okay? So if there's no charge there, they are equal. Okay? Now, how many neutrons?
132.
Correct. For that, ladies and gentlemen, we're going to take these two numbers in front and we are going to subtract them. So that means 133 are the number of neutrons. And then what would be the mass number here? 219. Sorry. The mass number is that number up there. Okay? So, Jimena, how many protons in this lead 211? 82. How many electrons here, Victoria? 82. How many neutrons here, Ethan? Not you, the other one, sorry. Okay, 11 minus 2. No, 11. 11 minus 2. 9. So then this would become 20 minus 8. There you go. Yeah, it's not an easy one to do, but we can get through it. 129. What would the mass number be here, Zoe?
211.
211. Questions, ladies and gentlemen. Okay? So that is the kind of thing that you need to be able to understand from that symbol. Questions? No, this is what I want. All right. So let's try it one more time here, ladies and gentlemen. All right. So this first element, ladies and gentlemen, this one right over here, number 1. Alex, how many protons?
Can I get the key to the band room?
Key to the band room to get those boots out of there.
Faith, you really should have been in class on Friday.
She had an apple for you.
Yeah, and an orange. You're lost.
Missed out again.
Oh,
Again.
Faith.
Again.
It's easy.
All right.
You may put Bukowski in here on Friday.
So back to it. How many protons, Alex? 92. How many electrons here, Jaslyn? 92. How many neutrons here? Kevin, sorry. 143. Mass number here. What would the mass number be, Lucy? $235. And what would the name of this be, Kiana? A little more.
Yeah.
You're-
Uranium 203.
Very good. Uranium 235. All right. So, Mariana, protons in number 2 here. How many protons in this element? What? Thank you. All right, Ethan, how many electrons?
3.
Can I ask how you got 3?
I bet. I did it wrong.
Okay. How'd you get 3 though?
Because I got it from the top number.
Okay, but that's not the number of electrons, is it?
Let's see.
Okay.
1.
I'm gonna take a guess and say it's 2.
You're going to take a guess and say it's 2.
Yes. I say that.
Why
because
2?
There's a charge of +1.
Okay. Which means what? How do you get to be a positive 1, Ethan?
You have to lose 1 electron.
Okay. So you have to lose 1 electron.
Mhm.
How many electrons did this atom start out with? If it were neutral, how many would it have?
0. Or
If it
1.
were neutral, how many would it have? 1. And this one has done what with an electron?
Or lost 1.
Good. Tell me which, because now you've given me both.
Lost 1.
There you go. Okay, so how many does it have?
0.
0. Has none. Has none. No electrons in this. Why? This charge is equal to the number of protons minus the number of electrons. To have a charge of +1, it has to be equal to 1 minus some number. That number has to be 0. Okay. All right. How many neutrons here? How many neutrons in this one? Christopher. In number 2 here. 2. Okay. What's the mass number here, Alexa? 3. What is the name of this one? What is the name of this one, Helen? Hydrogen what? Hydrogen 3. Very good, ladies and gentlemen. Questions? All right. Excellent work, ladies and gentlemen. All right. I want you to tell me what the nuclear symbol would look like. So take a minute, okay? I'll get you a scrap piece of paper here. Don't waste your own. I got plenty of scrap. Pass them down that way, please. So figure out from the numbers at the bottom now what the stuff at the top is. Again, if you don't need this scrap paper, that's fine. But if you do, here you go. Thank you, sir. All right. Now you got the information at the bottom. Now you got to figure out what goes up at the top.
Oh, so yeah, okay.
So this is easy. Like you take the proton on the bottom and then the mass number on the top.
Okay.
It should be that simple.
There you go.
Okay. Nobody said it had to be hard. All right. So what's the first symbol look like? First of all, what element is it?
Potassium.
Symbol what? Okay. What number goes on top in front? 40. The mass number. What number goes on the bottom? 19. So that is what your symbol should look like, ladies and gentlemen. Just like that. Okay, what's the name? The name is potassium 40. Okay, over here, what element is it?
Beryllium.
Beryllium. What number goes in front on the top?
8.
On the bottom?
4.
There you go. There's your symbol. What's the name? Beryllium 8. Questions, ladies and gentlemen?
Is there like a tip of how to identify what's the element with like?
Element is always based on number of protons.
Okay.
So if you give me a number, pick a number, Jimena. Give me a number. 20. You go up to the periodic table, here's 20, it's calcium. Okay? So as soon as someone gives us a number, give me a number. 5. 5 is boron. Okay? If that number represents the number of protons or the atomic number, that is how we determine what element it is. Okay? Questions? By the way, also once we know it's boron, we know its symbol is B. If you said 28, 28 is nickel. Symbol Ni. As soon as you know the number of protons, you can tell which element it is. Okay? You cannot identify it based on the number on the top. Only on the number on the bottom. Questions? Okay. So, this is what your homework is going to look like, ladies and gentlemen. So again, if this is the symbol, what would be the name of this? What is He on the periodic table? Helium. Helium 5, because of the number up here. What's the atomic number?
5.
No. 2. The number on the bottom here. What are the number of protons?
2.
Same as the atomic number. What are the number of neutrons?
3.
Subtract the 2 numbers in front. 5 minus 2 gives us 3. 2 electrons here, ladies and gentlemen. What's the mass number here?
4.
No.
Oh, whoa.
Where'd you get 4 from?
I'm wrong. My bad. I looked at the periodic table.
Don't look at the periodic table for mass number.
Yes, sir.
What's the mass number? 5. By the way, what's the charge on this atom? What's the charge?
Positive or negative?
No, what is it?
There isn't a charge.
There isn't a charge. It would be shown here if there was. So, since there's no charge, what's the charge? 0. It would have to be shown here, ladies and gentlemen. Now, the next one. All right. What is the name? Silver 110. Atomic number here. Guys, the only thing you need to go to the periodic table for is to look up the name.
47.
47, the number on the bottom. How many protons?
47.
47, the number on the bottom. How do you find the number of neutrons?
110 minus 47.
Subtract the 2 numbers in front. What's 110 minus 47?
63.
63. What's the mass number here? 110. What's the charge? 0. 0. Actually, that would be wrong.
Uh-oh.
Well, I have it wrong.
Uh-oh.
Because what do I have for the number of electrons?
46.
Which would make it what for a charge?
-1.
Nope.
Oh.
+1. But it would have had to have had this up here. And it doesn't. So this should have been 47. Sorry.
But we
Sorry.
can't edit that.
What?
Can't edit that.
Don't edit it then. Don't edit it. Just know it's my mistake. I'll take the blame for that one. All right, ladies and gentlemen. So, classwork. Here are your answer keys for all of the worksheets, ladies and gentlemen. All of the worksheets for the units that we are going to do. Here is the worksheet that is due today or that you need to work on right now, ladies and gentlemen. Again, it's a review of what we have been talking about. So here is the table that we were just working on. Okay? In here, the way I make this symbol, I use Control and the period key to do the superscript, Control and comma to do the subscript, and then I write the symbol afterwards. Okay? Then I write the symbol afterwards. Okay? So, unless it gives you a charge, there is no charge. No charge, no charge, no charge, no charge, no charge. This one's a +1. Okay? So, get with a partner, ladies and gentlemen. You got about 12, 13 minutes. See how much of this you can get done. If you have questions, please let me know. Yes, Ethan.
For carbon 14, I'm having trouble getting the number of electrons.
Well, what's the charge on it? Where do you see carbon 14, by the way?
Whoa.
Okay, if it doesn't tell you there's a charge, there is none. So what does that mean for the number of electrons? It's going to be the same as the number of protons. Remember, the only way an atom can have no charge is if your electrons and protons are equal to each other.
I gotta close this later. Because my computer's at 4%.
Well, there's a charger here you can use for the last 10 minutes, Zoe.
When I started class.
There's a whole entire another page on this worksheet, and I turned it in early. My bad.
Unsubmit it.
I just did.
You didn't get to the page I'm on even?
I know, because I saw.
There's not a whole nother page after that.
No, I mean, because off of the last question, what is the major difference between a nuclear reaction and a chemical reaction? It was blank, so I thought that was it. But then when I scroll down, there's a table.
No, because a lot of times if the table's too big, it puts it on another page because it won't split the table. If it kills you, I won't ever make you do it again.